I'm just here to report on behalf of a great team, led by Josh with his architecture group, but also lots of thanks to Derek and the whole architecture team and all the people that are listed down there who contributed actively, technically, and with their expertise in high performance computing and expertise from other domains. And when I'm standing here, I'm literally standing on the shoulders of giants. If there's anything good, what I present here, it's the people that are named around me. If there are things that you don't like or things that are awful, that's my fault, please blame me. This is like a strict job description, separation. Everything that is good, that's the team. And everything that went wrong, that's on my account. GNU Radio was and is a very big success. I'm like, how many open source projects do you know that live more than 20 years or more than 10 years? Most, they start off when they start a PhD, and once the PhD is over, maybe they maintain it for 2-3 years, and then most of them die out in obscurity. What Eric and others achieved was that there's a healthy community around it. That people say like, okay, we carry this on. This has a very strong buzz factor. Even, I mean, like buzz factor is a positive thing, that even if you run over one person, it still lives on. And that's also like our mission. We wanted to invest in this ecosystem. Maybe we could stem it ourselves, but we wanted to invest into this community, which is great, which want to use it, and leveraging the benefit from the diversity we have. And making sure that we have a strong buzz factor, so that we have maybe 7, 8, 9, 10 core maintainers that can stem and offload the responsibility. I mean, like while Eric, it seems to be like a one-man show, and he basically, if you would do it with one man like Eric, you could redo everything in one go, but our explicit goal was that we spread it out on more people, so that the burden of being up at night and fixing things that are critical for some of the organizations that need to be fixed, to keep it a bit more relaxed and fun to work with that. So in that sense, I'm but a dwarf standing on the shoulders of giants. On the bottom, Eric. On the shoulders are Josh and Josh and Derek lifted us up on their shoulders to show the community what's around there and helped us to get a better gauging the future where we want to head for. Importantly, why we invest in GNU Radio is it's a great ecosystem with a great community, but as any projects, many software code bases grow organically, like incremental, adding features here and there, sometimes always in the same line, but sometimes you have ideas that worked out as a proof of concept when you incorporated it, but when building upon it, you see like, oh, maybe now since I reached the top of the mountain, if I would have to go back to that mountain, maybe I take the more direct, easier path than the path that we actually took during the development process. And that, when I say like it's not a new development that we did. It's just that we took the experiences and the code base, so what's worth that we should preserve. And this is usability, this is the flow graph concept, that's the GNU Radio companion. This has to be the same because that's excellent. People love that, that keeps the entry level for normal users as low as possible. But there are also certain things that were necessary initially, which through new technologies, new C++ standard became sort of obsolete. And nobody could tell me like, why is this part of the code still there? I mean, it was a bit of archaeology. And then if Marcus told me like, I thought like, okay, it could be there's somebody else who uses this part of code. Well, that's important when there's like, okay, let's try without and see whether we can make it better without that. So we started with an organically grown tree and just removed a bit of the branches where we felt that they were excessive, so that we have a stronger core, that the remaining branches grow longer and survive not just for the next 20 years, but ever, and that GNU Radio is the best signal processing framework, full stop. Now, we have several modernization goals when we started off. I mean, like one is obviously simplifying onboarding of new contributors, because also our organization deals with lots of students, with academia, where people come in for half a year and they need to become effective to interact with radios and with our facility. But also for people who want to write blogs, that they can contribute more effectively without having to learn a very large, complex framework and to understand what the constraints are. So what's important for us is we wanted to rely on true industry standards. So we wanted to have as little as much as needed extraneous information that you have to get into the ecosystem, into the know, and to know what to do. We wanted to reduce the cognitive complexity because as you get older, I mean, I'm a very good code reviewer, even of my self-code, because after a couple of months, I don't even remember what I wrote. And if I read my code and I start scratching my head, why did it write that way? That's a good indication this code has to be refactored and simplified. Because if I have a problem reading my own code, then probably many other people will have the same. And this has to be, if you read code, it has to be obvious and on a very small scale. So you don't have to go through the whole code base to understand a small section of code, but the single source of truth is important. And yeah, reducing the learning curve. And yeah, to promote collaboration, knowledge exchange, and adoption, not just in the academia, but also in the scientific institution applications, but also to branch out to other organizations that are government funded or even industry funded. So that GNU Radio is not just a hobbyist or academia toolkit, but that this could be also used in commercial application. Because having industry on board is very, very useful because they provide because they have a large deployment of hundreds of nodes. And the more you get their feedback, you see what works well on a single deployment scale or where are the issues when you deploy hundreds of thousands of those devices. And this information is useful. And that helps us also growing a better SDR hardware ecosystem around that. And provide some continuity. So what is our main goal? And basically, I could stop here because I think everything is already said by Josh. But we want to preserve what is good and grow the existing diverse GNU Radio ecosystem. Python will be still in there. And there will be always a full thin Python layer over the C++ API so that you can use it in the most convenient way. But we want to make it more composable, more modular, and to opt in so that you only pay for what you need. So that you don't have to get in all the functionality that you potentially can use, but you just get that in what your application needs. And if you need some other extra, you can build it in. But if you don't need it, you don't have to pay for this eventuality that some obscure user like us, for example, needs. So without much further ado, let's show like an example. What is the hello world example for a simple processing block? And that's all that you have to write. Meaning there's no extra code generation, you don't need YAMLs, you don't need anything. You just basically write a simple struct, a C++ class. The only constraint you have is that you have to derive it from a CTRP template, which is called presently node. We will rename this. I mean, whenever you see a name that is a bit odd, that this node comes from the math branch of graph processing theory, where this blocks are called nodes. So we were initially not sure whether we should adopt a math terminology or adopt like the traditional GNU Radio block terminology. And for this one particularly went for node, but this will be changed. I just left it in this way because that's actually from the source code. So this is not slideware, that's copy-pasted from running as we have now. And if you want to write a simple block, you have to derive from this CTRP template, and then you define the ports that you need. And then you have an input port that takes in floats, you have an output port that takes floats, and then here you name them as you want to have them. In this case, it's one port called in, the other one out. And in this case, I said, like, I make a small basic multiplier, and so like I have a simple scaling factor, but this is just for explanation, for illustration purposes. And now what's different, before you had like the work IO functions where you had to do a lot of boilerplate code, taking the ports, unwrapping how many samples you have, and putting the samples back. In the simplest form, if you just care about signal processing and math, you just have to implement a process one function because you have just defined one input port. It has one input parameter, which is the const float reference to A. And as a result, you return a float. That's all you have to do, and the rest is done with the default implementation of the work function CTRP, and you're done. And the advantage of this is the code here is the code is a single source of truth. So if you want to know anything what the block does, you can derive documentation from that, you can add annotations, and you can very well test it in unit testing because we want to enforce in GNU Radio 4.0 a bit more that every block that is put in is production tested so that you can also use an industrial environment. And because of this, because of writing it as a sample-by-sample processing, this also allows us to skip buffers. Because the fastest buffer you can have in your signal processing chain is that you don't need a buffer. Because if you have one block, handing it directly over to the next one, it's the fastest way, and you just add buffers when you want to have those buffering capabilities, or when you have like two blocks depending on the same source block. You have noticed on the bottom there's like a small macro called enable reflection for. That's basically the compile time reflection that we added. This is something that we're working on with the ISO C++ committee, that the struct reflection will become part of the C++ standard, and that's, let's say, my sore eye. That's what we want to get rid of. So this is, for the time being, is still needed, but as soon as the ISO committee agrees that just this little bit of reflection should come in already now, because they have way bigger plans for compile time reflection, but if this struct reflection, field reflection is in, we can drop that. And it's also just needed, it would work without, but this is a convenient function so that we know that the input port in is actually called in. With this way, we avoid that we have to define a string, how the port is called. So yeah, what is, I hope I could convince you that this simplified a bit like the block development, because it allows like a standalone creation, is hopefully much more intuitive, and the code is a single source of truth. If you have issues with that or questions, please let us know. I mean, like, this is not contractual. This is a software project where soft means that we can modify it, and we can iterate upon that and make it more intuitive, or better, find a better naming. And that is more efficient also for functional testing, what I said. And this function, process one, is actually the one that is most efficient for the compiler to optimize in larger scales. And because you can test it during compile time already, you get an earlier warning if something is wrong in your block. So you don't have to run the block always through the flow graph and test it until you have a runtime exceptions, but already it will tell you during compile time there's something wrong, fix it. And this should ease up the iteration cycles. Okay, now you realized I cut a bit short because float is important, but I want to write a block for any type. That's now a feature for where you first need like really C and not just C. And then you can use with C++ a templating. That's the standard. It exists already since decades. But with the C++20, you can constrain on what type of types your block is allowed to process. In this case, arithmetic, so any mathematical object can be used. But you can also write blocks with a new buffer that can have any arbitrary type, even like aggregate types, structs. The only requirement is that they're either copyable or movable. That's all. And then the structure stays the same. You don't have to write multiple blocks for multiple types, but it's just the templated process one functions, and you're happy camper. Now, some people might say, yeah, but this doesn't feel kosher. Processing one by one, that's inefficient because, or maybe I swap in and out and have like cache line invalidations. I want to have more something like a process, like a bulk-based processing, where I get a large array of input samples and I give out a large array of output samples because I want to use Volk, and I want to, or I have an FFT where I need, for example, 1024 samples in order to produce one out. And for those, we have an alternative version, which you can also use. The CRTP template, it recognizes this automatically. And then you get basically a span, which is a glorified array for the input and output, but the span is a non-owning type-safe way, which is recognized by the compiler and can optimize for that. And then you can, in this case, I used the range library. This is now where you can process it with the transform function, which is multiplying. It's basically the same what I did before. The advantage of transform is they can also use, it's automatically SIMD-fied if you use transform internally for the next library versions, for the C++ standard lib library versions. But you can also do parallelization if you say, like, I want to use the new executor policies for C++. Now, sometimes, fun fact, beware. Initially, this was an input from Matthias Kretz. He's the lead for the ISO C++ standardization committee for numerics, so for our high performance guru. And he proposed this process one. And he said, like, that's way more efficient. And my gut feeling, and hands up who would think same way, so like, no, that's never gonna be fly off. That's slower than I loop over my array. I was one of them. But fun fact, one has to be sure of premature optimization. I was skeptical. We implemented the both versions in parallel, and in the end, you shouldn't only assess once you actually benchmarked it yourself against a real use case. And I lost. Not only is the process one not less efficient than this, but it's even 20% more efficient than writing the old code, the old style. And I thought, like, okay, there is some gains. So you can have, from a human conceptual cognitive complexity, write simpler processing function, and you get more speed. So win-win. Now, you still have some applications where you need process bulk, but as a number of samples, but you're not sure whether you produce the same input as output samples. For example, I want to consume 1,000 samples, but I produce just 2. So you have like a decimator or interpolator. And for this, you can either use the process bulk, and then you can have a consumable span and publishable span as your function signature. You just have to use them, and they're automatically being invoked by the block API. And then in the end, you can do whatever processing you have and say, like, from the input, you can give me all, but I just consume 3. So the buffer assumes just take 3 and the rest stay in the buffer, and you publish 2, and then the rest, next time it's invoked again, you get the remainder that you have there. And with this, you could do like a decimator, for example, or an interpolator. Equally, or you can even do something random ways, so like depending on how many processing logic, like if you want to write a PLL, sometimes you don't produce any samples, sometimes you have an arbitrary number of samples. That's the API for that. If you just want to do a decimator or interpolator, you can have it easier, because that's still verbose. You can reduce this, and you can see on the top right, you have like a performance interpolation. This is like an NTTP, where this is optional, you don't have to, because if you don't use this, then you don't pay for it. But if you use this, then by default, you can tell the block in advance, either as a compile time parameter or as a runtime parameter. Please instantiate this. You say the numerator is 1024, the denominator is 1, and that's basically runtime configurable decimation block, where you take 1024 samples and you reduce 1 out. If this denominator naming is not ideal, please let us know. This is all subject to change. We can adjust on that. You can set also later the stride. If you say, like, I want to skip every 10,000 samples because you want to take an FFT of 1024, but take every 1 second, then you can also apply a stride. And alternate, you can also access the block parameters directly. Then, because we have like 2 copies, one is the block, the single truth is like the block, but then you have to transfer it to the PMT representation. For that, you have to update the active, also invoke the active parameters to synchronize both representations. In the other way around, you don't have to, but if you do it manually, this way you have. But it's normally done automatically. And this is a big shout out to Simon Lebedev, who built this interpolator and striding block. Works fine. If you ever see him, please buy him a beer. The thing is, like I showed a bit like a setting, like the numerator is a setting. Again, the same application, you want to sample, multiply by A. Now we went back to using the process 1 because it's more efficient. But sometimes if a setting changes, you want to change other internal factors of your block, because you say, like, whenever somebody changes a parameter, I have to reallocate, reconnect to the device, make some other changes. And for this, you just have to define an optional settings change function. So the name is enforced with concepts. And then you get as an input, like a const reference to the old settings, and a const reference a property map, which is a map of PMTVs with the new settings. And then depending on the old versus new state, you can trigger whatever action you have. You can reset the block. You can allocate new buffers, clear buffers, so you know whenever a setting occurred. And this is optional. You don't have to implement it. And it's also not overwritten. We have like several updating mechanisms. You can either do like a thread safe getter setter on the block itself. Something that I'm very proud of that works quite well. You can also set settings via streams. For example, if you want to set the sample rate, you can set an upstreams block. Please change the sample rate, and that is then propagated through the whole chain, so that all blocks that are in the subsequent topology can update the sample rate and act modify the block structure so that you don't have, in our case, we have up to 1,000 blocks in a row. They're all updated automatically. You don't have to iterate through all of them. You can disable that if you don't like this and still do one block at a time, or select, please don't do auto update, but by out of the box, this is done automatically. Or you can also use async messages. You have like as Josh said, we have like the buffer doesn't distinguish between whether you do synchronous or asynchronous processing. Each of the block will have also like a message in, message out port, where you can send a PMT message in for reconfiguring the settings. This you can also use for packet-based processing or send any other logic that you like. So you have either one function is called synchronously, where it makes sure that all the input ports have the same number of samples, and the other group of ports, message ports, they invoke your callback function whenever something arrives, and then you have to tell something is enough, or no, please go back. I just act upon when my message port have a certain precondition met. Yeah, and here's also like a big shout out to please buy him a beer for his great work on PMTVs, because that all is based on his work, and makes it much easier also to wrap to Python, or to make it, to send it from one architecture, one node to the next, because this is now, independent on the architecture where you generate this. This is just some examples. This is like a pre-production code, pre-production because this is, we don't call it officially GNU Radio 4, this has to be evaluated, but that would be basically a full FIR implementation in the new API. And I showed it just for the sake, you don't have to read all the slides, but just the fact that it fits on the slide is a big achievement, because before the code was 5-6 times as much and you had to be very intricate. But you can see you just need to apply the input-output ports. You get notified when the settings changed. It also shows a bit like how you handle with input and output histories. And the actual function on the bottom is just a std, like a std algorithm, std inner product, that's all. So you have just one line to implement an FIR. And I think this is how it's supposed to be. On top you can see there's the code, like code documentation, where you either can provide like some HTML pages, or for your UI you can say the writer of that code documents inside his code what each parameter, what each function has to do, and this can be then used in the UI to display how to use the code. And you can inspect that without having to launch from a developer point of view, without having to launch the GNU Radio companion to see how it looks like. This is like Markdown enabled, you can already look in the source code. So this simplifies a bit. The same for the IIR. Then we went a bit out, because for IIR you have like 4 different possible implementations, and for thoroughness we said like, let's do all of them, and then you can choose which one you like. There's certain pros and cons for each one of them, and this is also fast, and this is also like a test bed for Matthias to see whether the new C++ standard can also improve the IIR for SIMD, because it's not quite trivial for SIMD, and this is like a test case. But this is already the standard implementation, which is fast enough. Now, note for the eagle-eyed, this is not your dad's C++98 anymore. We use stun std only features, so we minimize the library dependencies on any other libraries other than the standard one. This is just to be easier in terms of portability, so that you can run it on embedded and also high-end computers equally, or even on your mobile phone. And while we try to use as much C++ possible, if it helps the readability and the conciseness, some features, especially ranges, we held a bit back, because we want to make sure that when we use a feature that is worthwhile and that it has to be supported by GCC, Clang, and MSVC. This is just to improve portability. Clang for the reasons because we want to be able to compile into WebAssembly. And if you want to know about, because C++ receives so much love from you, I invite, there was a very great talk by Daniela Engert on the last year CPPCon2022, like about contemporary C++, and I don't want to make more advertisement, but just invite you, have a look at this YouTube video. I think she did a great talk, and after that, I felt like, what did I do wrong for the last 25 years? So it shows really the prowess and the nice things in C++ that you can do these days. Nevertheless, Python is still core. Now, about Python. Basically, if you accumulate all the different requirements, you get, of course, a phone, for example, that can do everything. the bottom line is, from while we developed the core as C++, we didn't put Python back on a back burner, but we say like this is not an issue because making wrappers around the existing API is trivial. And we can reproduce the same API as GNU Radio 3.10 as of now. That's not an issue. The question is now, because we're starting on a green field in some point of view, do we want to do the Python development the same way as we have been doing it now? Or is there a possibility of improving it? Is there something where you say like, oh, if I could, this writing Python code as a block would be better. For example, if you like, say, I like this process 1 and the process bulk function just being exported, we could just export that. I'm like, there's several options. We can do it as before. We can use the reduced equivalent of what we've done on the C++, or you say like, no, having a dedicated Python wrapper is not that important. Now with the PyPy binding where you can generate Python binding on the fly and always of that function that you want to have, this is sufficient enough. I don't have an opinion on that, but we need your feedback on that because please get in contact with the GNU Radio architecture team because this is an open design and we want to make it at least equivalent or possibly better. And for this, we need your feedback, whether you want as before or better. Now, I hope I put some of your fears at ease. While the low-level code base changed, the overall course functionality stays the same. I mean, it's still the same processing framework as we love and use. But we cleaned up some of the internals, where most of 90% of the end users will never ever get in contact with. Now, some of the design principles from a high level, we all talk about software-defined radius. Software must be adaptable to frequent changes. That sounds obvious, but what does it mean, soft? Soft is very critical to this. Because fewer are library developers, more are application developers, and most are application users. And this we have to keep in mind and always remind ourselves, we all need to know what, when, and where functionalities were implemented, and we have to share the same terminology. And remain mindful also about non-RF engineers and other applications. And the goal is that to first order, we want to have an intuitive design where you don't have to explain how to use it, but people will figure it out by themselves or can. Nevertheless, we have documentation for that and examples before domain language and before the documentation of concepts. And basically, one important thing is like mechanical sympathy. I think that's at least in our domain why it resonates so well is because GNU Flow Graph replicates very much on how RF engineers build their own equipment, where you have like discrete blocks that are connected with SMA wires and label their inputs, label their outputs, that even if you can't program, you can understand the topology, how the signal flows through this. And maybe I should calculate the complexity, the GRC complexity for this flow graph once, but it's hopefully low. Now, what does it mean? We want to favor composition over inheritance. As you see on the bottom left, many of the processing frameworks are more like libraries where you can exchange components, but the boundary conditions are almost, let's say, constant, and you have to respect the API. We want to make it more a loosely based library where you can pick and choose which part of the components you want to use. And then if you don't want to use component, you don't have to pay for it. You don't have to pay the penalty, neither in code size nor in performance for that. So the modularity is very important. And to show let's go a bit very deep dive in why this is important, why we also used not virtual inheritance. This is a compiler explorer example left with virtual inheritance and right with the new concept. You can see the assembler that is generated is 10 times more than with the concepts that we use. And the problem is that as soon as you use virtual inheritance, the compiler can't see through the virtual inheritance because it has to assume that any function can be replaced during runtime. So each function that is virtual is potentially unsafe. And thus the compiler has to make very unsafe, very safe choices, optimization choices. And that slows down the processing a lot. And we try to minimize this as much as possible. But we still have some virtual inheritance where, for example, the plugin system for runtime where it's unavoidable. Now, some clean code-based design is like documentation. Basically, you annotate the code, you annotate the block in code. You just add some small strings with an annotation class, and then basically that carries along also all the information that you need in the UI, whether you want to see a port visible or not. You can also do like language translations in there. This is an API just as a proposal. We can still change the order of priorities and adding some more better defaults. But yeah, as you write the code, it's documented. And we can also parse and then generate, for example, without you having to modify any other files, we can generate some text output from that. So now the bit juicy is now this is like the API, nice API, that's good and fine, but is it worth to go that? Because just nicer API doesn't convince anybody to switch over to a different way of doing things. The new buffer is basically lock-free, thread-safe buffer, which can be used as a multiple observer with the classic. We used our own implementation of the disruptor pattern, which we stripped down and made it to replicate also the GR use case, where you can have this classical use of a fan-out, one source feeding several things. But you can also this fan-in, which is used for messaging. It's the same buffer, so not two implementations, the same code base. You can do also message passing or like a message network. It's the same buffer without changing. It's just on whether you allow the blocks to have multiple inputs, outputs. It's the same. And in the message, we decided on using John's PMT maps. Or you can also do multi-cascade, that you can say several blocks share the same buffer so that they do in-place modifications. And you can have multiple changes, so you don't have, you conserve a bit on your memory footprint and performance. And you can also omit the buffer. For example, if you have a linear cascade, you can write a subgraph, and the subgraph is then executed on this process one, and is handled as one single block. And that was important for us, because sometimes we have very basic operations like ×2 times a certain linear functions minus some offset scaling, and then you have a chain often of 10, 20 blocks. With the old scheme and with the push-pull system through this microservice architecture, we had a very high latency, because every mutex that you hit, you get a penalty of 100 microseconds. And if you have hundreds of those, 100 times 100 microseconds is slow. And if you want to have real-time applications with less than 100 milliseconds latency, you don't want that. That's the reason why we put in the low latency or no lock-free buffers. Yeah, the reasons why they're hopefully positively perceived, it's type strict, but you can pass any type that respects copyable, movable, and if you want to do yourself a favor, make it cache alignable, so you have to be a multiple of 64 bytes, because then your CPU will treat you nicely in terms of computing performance. And yeah, this simplified the async message. How much am I in time? Okay, this is the performance improvement. Red is in the old, the 3.10, and in blue the new ones, both for the POSIX compatible one and for with the portable one, which also works on non-POSIX systems. And we got at least a factor 10 improvements just for the buffers. Main reasons is, because we use atomic compare and swap paradigm and the type strictness, which the compiler can see and can optimize a bit more. Now, the second thing that we added was performance optimization is out-of-the-box single instructions, multiple data operations. Maybe some of you know this. It's basically you have one instruction, and for the classic programming, if you do virtual, one instruction, one data reduces one results. But the SIMD is basically that you can put in multiple data and apply the same instructions for all of the multiple data and get multiple results. And that basically quadruples, in this case, your throughput performance. And this maybe in the early 2000s this was not as appealing as possible, because for most of the architecture here used like the Intel, you got maybe a performance boost of a factor 2 if you're lucky. But since 2012, 13, you can get a performance boost with that at least of a factor 4 up to a factor of 16 nowadays. So if you don't use SIMD in your algorithm, then basically you only use 7% of your CPU. So you have to use SIMD, you have to optimize for your architecture. And then the question is like, how do you do that? So there we got adopted by Matthias, who's the main author and lead for SIMD integration in the C++ standard. And he wrote this extension for us. This also allows like compile time merging of blocks, where we can forgo the buffers and enables the compiler to see through and optimize the algorithms. And here I have a bit of like a small benchmark. On the top, you have like the merged comparison with the bottoms. Maybe you look at first, the first one, source to sink, is a simple graph of one source, one sink. you can see on the top right, we get a throughput performance of about 16 gigasamples per second. This is a bit academic, but this is mainly the memory bandwidth that you have and the cache bandwidth that you have. But this shows a bit like the overhead of the benchmark. But the interesting ones are the ones highlighted in blue, where you have a cascade of a multiplier, a divider, and an adder that is repeated 10 times, one after the other. If you do the compile time merge, you get about 250 megasamples per second throughput, which is very interesting because that's the throughput that you can get over USB 3.2. So basically, you can process all the data that you can push from via USB 3.2 in one go for a very long chain of blocks. So you can do really serious real-time signal processing and then feeding it back to your transmitter. If you don't do this, you drop to 80 megasamples per second, which is still respectable. This is still a factor 10 faster than the GNU Radio 310, which at that I forgot to clock, but we're talking about 2 or 3 megasamples per second. So that is still a huge improvement. And one small highlight, this is the example of the process 1 and process bulk. That struck me, and you're faster with that. That's not the end. With the merging, also the runtime merging of blocks, some of the use cases, we should be able to bump it up a bit more. Here, like a big shout out to Dr. Matthias Kretz. Here I name explicitly doctor because he really deserves it for his work on it. He's really the doctor on SIMD. And you should buy him a beer and support his paper and give him a shout out, a thank you when he twitters. Now, tag-based timing integration. We often deal with MIMO systems. If possible, normally you synchronize it via the same RX channel being on the same DAC. That's not always possible. On our side, we have a fairly distributed system where our SDRs are distributed over 4.5 kilometers. We won't route analog signals to the same SDR, but we have to synchronize them nevertheless. And this real-world problem, how do you resynchronize physically spatially distributed sources with the same flow graph? And in the end, the solution was very easy because we already opted into tags. We just said by conventions, we generate 3 tags that all sources should produce. This is the trigger name, the trigger timestamp, and the trigger, I forgot, but just 3 tags. And these are then attached to the sample where the digitizer recognizes this, and then they're propagated through the whole network for each of the nodes. And then you can have a synchronizer plug in and say, like, please buffer the samples until this trigger synchronization tag arrives. And then you push further on with a synchronized stream, and then the rest is synchronized as you want. And in our case, we are the co-developer of White Rabbit at GSI Fair. And integrated. That's actually all. It's now out of the box. And actually, once we've discussed about it, this was useful for the several iterations we had. It's a very simple and beautiful solution. So there's some another advanced processing features where I go through this. Okay, we use the digitizer. I showed this in the talk yesterday, a bit of modernization. Initially, we had like 2 ways how to process data, sample by sample and chunked. I think I skipped this because that's obvious why it's not important. Important is that we have like 3 types of acquisitions, sample by sample, chunk-based, but also we have transient recorder where we basically continuously monitor data, but sometimes if we see an interesting event, like if a plane crashed or we created a microscopic black hole, we want to document it for posterity to know why it was created. And we have to be precise. So and for this, we need like 3 different types of processing, which by adding this tags, this basically makes it very flexible because you can use this tags to copy and paste certain segments of your samples, and they're propagated throughout the processing chains, and then you can make data sets, which are basically aggregate, which are a bit like SIGMF style data sets that are annotated and then can be further post-processed. And you can also cut and paste certain subsections and then do multiplexed acquisitions. And there we have, in our case, we implemented multiplexed processing, 2 different types, also triggered with for transient recording, or the simple continuous acquisition as GNU Radio does now. And you can do other fancy function-based processing. You can take a segment of acquisition and can treat it as a function and do like a discriminator or transient detector, and then can, like Cinderella, you can divide the good data sets from the bad, have 2 different things, write them into different parts. You can also make feedback loops. I mean, like the original limitations of directed non-acyclic graphs is dropped. We can do feedbacks now. And yeah, this is a small overview of the packet structure. So we have the same structure for datasets, packet and tensors, which largely will replace the old PMT message, not the PMT, PDUs, sorry. But it's like basically the same design and simplified a bit. In the future, we thought, like, since we can do already asynchronous processing and block-based data, maybe we can go somewhere in the same direction like Unity control system and also make like some other high-level blocks for making more advanced processing, or even like UI designs if you want. And at least on our side, for our UI, we will explore that direction. So broaden cross-platform support. This is like, because it's very important that you not just develop a library, you have to also see whether it works in the application. So we have like the full vertical stack. And we have an emphasis that this framework or this library is supported by GCC Clang and Emscripten so that we can support WebAssembly. And we have like a small tech demo that GNU Radio also runs in the web, a new web browser out of the box. Now comes maybe the other interesting part, the juicy. Sorry, I'm running a bit, maybe 3-4 minutes over, but this is really important. We all know that we need like a more flexible scheduler, and depending on the domain or depending on the different topologies, you have certain subgraphs where you have different scheduling priorities than for other subgraphs. For example, if you have a subgraph that should be executed in the GPU, you need a different policy than on a CPU, or if you want to have throughput optimized or low latencies, you need to change your scheduler behavior. And there's not one single silver bullet solution for the scheduler. You have to specify for this part you use this paradigm, this policy, and for this, the other one. And in the old specification, this was basically handled as a microservice architecture, which is a valid construct, but it always involves push-pull mechanism that's very inefficient in terms of data processing. And we flipped this like 90 degrees around and said, like, we make now a work scheduler where the work functions is, because every CPU can only execute one function at a time. So we optimize the execution of the block of the flow graph so that we maximize the utilization of the available computing cores or the latencies. And then you can have, for example, a scheduling domain for the CPU, augmented with a scheduling domain for the GPU. And then depending on your necessities, have different boundary constraints for these. And yeah, the reason is we have like, there's not one single good solution. Unfortunately, can't go into this, but have a look at the slide later. We made some topologies that are specifically designed to trip out schedulers, which are hard to schedule, where we know that the traditional schedulers will get into their knees. And they have different policies, and the exercise here would be, if you have these blocks, in which order would you execute them with a given number of sample constraint, and you will find that they're, depending you want to optimize throughput or latencies, the order execution is different, and you have to optimize your scheduler for that. Same as like another topology is when you have two parallel branches. If you have a feedback branch or like a path that terminates earlier, how do you handle that? Do you want to sync 1 and 2 arrive at the same time, or do you say like, oh, I have data already sync 2, please give me this earlier than the sync 1? Or this funny one, where many people say like, nobody uses this type of topology of graph processing. Who uses AI in their flow graphs or in their applications? Nobody? Oh, okay, there. I guess you recognize that's basically an artificial neural network, nothing else. Now we can do this also with high-level blocks in GNU Radio. Now we didn't, because there's hundreds of different possible implementations, we didn't implement each and every scheduler possibility. But we did, we started off with the busy looping with this naive implementation, like the old or the simple version that was also implemented in the new 4.0 version. Then we implemented depth first and breadth first. This comes from graph theory, just to make sure that the API that you need for writing your own scheduler is sorted out and that it works and as a proof of concept. But there are many, many other possibilities. We documented them in a README. Each of this is like the most common scheduling topologies, and there's still active research. Just by the sheer number of lists, you can guess it's not obvious one which is the best. And the next step, what we wanted to do is like to have a healthy competition, like a block coding party where we invite everybody here in the States and back in Europe to flesh out all the missing blocks. And then accompanied with that is like a competition. Who writes the best next GNU Radio 4.0 scheduler? and have a bit of, for the topologies that I've shown, maybe some additional one, write schedulers that can detect and automatically optimize these topologies and give the best results for the boundary constraints that we set. And then it's like a healthy competition, and the winner or the winners will become then the new implementation. So the example implementation was done by Alex. Big shout out to Alex. Please buy him a beer. He did a tremendous amount of work. Initially we thought, like, how hard can that be? And he spent a fair amount in making this work. And we all, I guess we can agree, we all learned a lot about, not just about the theory, but also how to put it into practice. So the overall project direction, I mean, I think Josh said most of this. We identified most of the HPC limitations and therefore 0. I think we addressed that. Next, for the staff prototype, unfortunately, we couldn't deploy everything for this conference because we rather said, like, do it right than do a quick hack. So there's still some refactoring to be done to make it easier, better looking. But this is, I hope, a couple of days or within a month, we can transfer this also to the from the graph prototype to the regular GNU Radio repository. And yeah, we're all based on the present GRC integration, so that we use the same file description. And we want to now also tackle the Python integration, but there we would like to get your feedback to see status quo or the new reduced interface, which maybe is easier for 90% of the users, or also in any other direction. Another thing that Josh wanted to address, but I think this goes now out of scope, is the next frontier would be also we know how to integrate GPUs. That's is fairly easy. It is more like a deployment and toolchain question to make that streamlining. But the question is, like, how to integrate also FPGA efficiently. And there's some ideas, thought, and requirements. So that's what I glimpsed through a short amount of time. And thank you.
So, thank you, Ralph. And I just wanted to highlight tomorrow we will be having a panel discussion, which will be open to a lot of questions, a lot of interactive discussion about what are the next steps for 4.0.